Hello class, today we're going to talk about transformations of logarithmic functions. So I want you to recall that logarithmic and exponential functions and how are they related to each other. A reminder that they are inverses of each other. So, and when we talk about inverse, we're talking about reflection across that mirror line, which is the y equals x line, like here. Right? So here is the exponential graph in green, and here is the logarithmic graph in orange. Okay? And when we talk about that, we're also talking about how in the exponential, we're inputting the x value, which would have been the exponent, and we get the product, right? And now in logarithmic, we're going to switch the input with the output. So therefore, instead of putting an exponent and getting a product, we're given the product and we're trying to figure out which exponent it is. And that's what you're doing when we do the inverse. So when we look at, for example, this exponential function f of x equals 3 to the x, and we compare it to its logarithmic version, which is log base 3 of x. The input of the original exponential function is an exponent, the output's the product. And so when we look at that graph, here's just a quick sketch. Our x values can range from negative infinity to infinity, and our range goes from above 0 to infinity. When we do the logarithmic function, we're doing the inverse of it. So the input now is the product, right? So we know what the final answer is. And what we're looking for is the exponent, and that's our output. And then therefore, a quick sketch of that looks something like this. And therefore, our domain is now from 0 to infinity, and our range is from negative infinity to infinity. So again, we see that switching between our input and output, and therefore our domain ranges change. A reminder that we're only ever considering exponential functions where the base is greater than 0. So this value here has to be greater than 0, so it can't be negative or 0. And therefore, the same goes for our logarithmic function down here. Okay? So let's look at an example. If we were to graph the exponential function of y f of x equals 2 to the x, and we compare it to its logarithmic version, or the inverse, let's do a table of values of the original base. We input x values negative 1, 0, 1, 2, 3. And so if you think about 2 to the negative 1 is really 1/2. To the 0 is 1. To the 1 is 2. To the 2 is 4. And to the 3 is 8. Okay? And then I draw it in purple. So here I have it here. And purple is all those values drawn out here. And therefore, if you see this exponential curvature, you understand that therefore there's this asymptote here at y equals 0. Now, if we take the inverse, that means we're doing the logarithmic equations. So when we do log base 2 of 0, for example, if x value is 0, well, what that means that 0 is the product, 2 is my base, so what exponent of 2 would produce 0? Well, there is none. So there's no exponent that would produce a product of 0. So therefore, it's undefined and therefore creates an asymptote. So in this logarithmic function, I actually have this asymptote here at the y-axis, which has the equation of x equals 0. And then when I continue doing it along the way, I get 0, 1, 2, 3. So I have this green logarithmic function graph that's drawn here with its asymptote, vertical asymptote now at y equals 0. And so you can see the exponential and the logarithmic function are kind of a reflection over this mirror line of y equals x. Okay, so now what happens if we're given a graph, a logarithmic graph such as this one? How can we determine its equation? Well, here are some things you would do. You check to see, is there a horizontal shift? If there's a horizontal shift, the vertical asymptote will move left and right. Well, because this vertical asymptote is still at x equals 0, there has been no horizontal shifts. Then we ask, is there a vertical shift? Well, just like in exponential graphs, there's always that key point. So in exponential graph, there's always that key point at 0, 1, which is a y-intercept. And the logarithmic parent function would also have a key point here, but it's on the x-intercept of 1. So then when we look at this graph that's given to us, that x-intercept still exists at 1, 0. So therefore, there has been no vertical shift, because if there was one, it would now move, and the x-intercept would be either closer to the asymptote or further away as this shifts up, right? So if I were to shift this up, I'm just going to do a quick sketch so you can visualize it. If I moved it up, look, now the x-intercept's over here. If I move it down, my x-intercept would be over here, right? So that's how you can tell if there has been any vertical shifts, is looking at the x-intercept. Okay, what about a vertical dilation? Well, vertical dilation, if you think back to an exponential graph, if I were to dilate this, I would still have my what was your y-intercept at 0, 1 here, but it would just look something like this, where it will just be lower or go higher or go further away, like something like this. Okay, and so since but that point of the y-intercept would stay there, and so similarly, a logarithmic graph, if it was to have a vertical dilation, it would still be here, but then it would curve further or farther away. So what do we have to look at then? Is that we have to look at, okay, what's our base parent? Well, a base parent, if we look at the y value of 1, so when the exponent is 1, the base would be 3, right? So if you think about that, 3 to the 1 is equal to 3. So that gives you your base parent. So when the y value is 1, that gives you your base parent here. And then therefore the second value, our y value of 2, would therefore be at 9, which it is. So because this is following the curvature of 3 to the x, or log 3 to the x, there is no vertical dilation, and so we can just say that the equation of this graph would be f at x equals log base 3 to the x. Okay? All right, so what happens if we are given the equation? Here we have this f at x equals negative log base 3 to the x plus 4 end bracket, and then plus 1 at the end. Well, if I had to state what all the transformations are, think back that this is our function here. So in front of it is a vertical stretches and compressions or reflection. Inside with the x is always horizontal, and then outside of the log itself, like this plus 1, it's a vertical shift. Okay, so if I follow that idea, I would say that there's been a horizontal translation left for, so the asymptote will move. There's a reflection over the vertical, over the x-axis. So that means that it's no longer doing this, but it'll be doing something like this. And there's been a vertical shift up 1 because of that plus 1 is outside the log function here. And you can tell that because there's this bracket here, all right? So that's the log subscript 3, and this is the actual product. Okay, so I would take some values, knowing the original base parent is log base 3 of x. So therefore 1 would be, for x value of 1, it's 0. When x is 3, it would be 1, 9 to 27, 3. And I know this because I know that 3 to the exponent 1 is 3, 3 to the exponent 2 is 9, 3 to the exponent 3 is 27. But now I have to apply these extra transformations. So I want to subtract 4 from my x's, do a negative y for that reflection, and then add 1 for that vertical shift. So when I do that to all those points, I get these, and I draw that. And I already knew that my asymptote had to move left 4, so I would have drawn this asymptote right here. Okay? And then do you remember we're going to have to still remember all these questions like instantaneous rate of change. So maybe I want to know, how is this curvature happening at the x value around 2? So that's somewhere around here. So I would use my IROC formula, and I would put that, and technically IROCs are all approximation because we're just looking at before or after that point. So I'll do 2 is my x, so negative log base 3. I put 2.001 plus 4, and that comes from the equation, the plus 4 there. But my x is now 2.001, and then plus 1. But then I have to subtract f at x when x is 2. So I do subtract negative log 3, 2 plus 4, and bracket plus 1, all over our range, which is 0.001. And then when I do this, the positive 1 here will get canceled with this positive 1, because this negative, don't forget, has to be applied to that negative 1. So it becomes really negative 1. Sorry, that negative applies to the positive 1, so it becomes negative 1. So that's gone. And I'm just trying to make this nicer for my calculator. So I simplify here, and I end up getting an IROC of approximately negative 0.152. All right, now on to the challenge. If you're given a logarithmic equation such as this one here, f at x equals log base 3 of 9ax, to me, that tells me that there has been a horizontal dilation by a factor of 1 over 9. Remember, this is a b value, so it's always the reciprocal. So that's what this equation tells me. But I can use log laws, or laws of logs, to find another function, another equation that actually give me the same graph. So if I were to graph that one, just doing a quick sketch, something like that. If that's my f at x graph, I can come up with another equation that actually will also map it out the same, but have a different transformation. So if you recall log laws, remember this is a multiplication happening between 9 and x. Well, that means that therefore I can add the addition of log. So log base 3 of 9 plus log base 3 of x. So here we have two separate logs. And I know this answer right here is just 2. So 3 to what exponent produces 9? Well, that's simply 2. So now I really have 2 plus log base 3 of x. Well, I can rewrite this really, if it helps you visualize it, that it's also the same as saying log 3 base 3 of x plus 2. So now this tells me, according to this equation here, of, I'll call this g of x, this equation says, oh, that's actually a vertical shift or translation up by a value of 2. And so it turns out I haven't changed the equation, I just changed the way it looked. So this equation and this equation would give me the exact same graph. Okay? Two different transformations. One was a horizontal dilation, the other is a vertical shift. And so I can do that with another equation. Here I have been given the equation g at x is equal to log base 4 of x squared. Well, using laws of log, I can bring this exponent down. So if I bring that exponent down, that now isn't a different transformation, because now this is a vertical dilation by a factor of 2. All right. And that's what you're going to have to do. So for homework, you're going to play around with some of these graphs. And if you have any questions, make sure to ask. Good luck.